bottom waveform is voltage on this capacitor, and voltage on this resonant capacitor here, because you see there is a loop. In this loop, because there's only resonant inductor or resonant capacitor, it's one of those things that consequence and a cause are mixed together. You see, the reason because of this, how this works is that in this loop, this inductor is volt-second balance, flux balance by the ripple on this capacitor. But in this loop, by definition, what it says, this capacitor DC value has to be 0. So this capacitor voltage, instantaneous DC value is 0. It is dictated because it has this resonant inductance is contained to be flux balance only during this on time of the switch period. And therefore, what is left is that the voltage on this capacitor is a ripple, which has a DC voltage and this ripple. And what is now the flux on this little, why this resonant inductance is little? Because it is flux balanced by a ripple on this capacitor, which is, you can see delta V for half a period and minus delta V for the other period. You get it now? Why this resonant inductance is small? Because this ripple is a magnitude of this delta VR is compared to VR, 1% or 2%, maybe 5%, but still 20 times smaller. So therefore, this flux is 20 to 100 times smaller than the flux on a PWM inductor. Therefore, this resonant inductance is small and does all the work. And that is the essence of this, why I call it the hybrid switching. Hybrid switching method basically says, in this case, during off time, converter operates like a PWM converter, deductors operate like PWM converter, and they have and capacitor has a, how you say, the linear ripple, which is on a switching converter. You have DC voltage and you have a linear ripple on a capacitor. But what happens with the ripple on a capacitor during the resonant period? There is a resonant inductance which is large magnitude, but the ripple on this resonant capacitor is switching between positive and negative ripple on a capacitor. So still the same ripple, but different waveforms. During on time, you have a resonant voltage, and during off time, you have ripple on their capacitor, same capacitor. You see, there is continuity. This capacitor is the same capacitor, but it's called resonant capacitor during on time, and it's linear capacitor during off time, because this is a PWM operation during off time, and during on time, it's a resonant operation, okay? So you see that everything is fine. So you have this, this operation, and if I go to here, let's see. Yeah, you see here now, during the on time, you have this operation, and then during the off time, during off time for negative part, then for negative part, this capacitor is discharging to the output, but in a resonant way. And resonant way discharges it get not lossless. And this capacitor being much larger than this in magnitude, say, then these two capacitors in series are dominated by resonant capacitor. Why that's important? Because then you have a single resonant. You don't affect changing resonant because this capacitor doesn't matter. You have the same resonant during on time or off time. Okay, and that is what is here. So if I go further down, so that is again operation that in this off time period, the DC voltage on resonant capacitor changes. It's equal to output DC voltage, but still same works. That has a ripple which is providing resonance with this capacitor. You understand? So therefore, it works for both cycles. And therefore, this is for on time, for a positive part of sinusoidal voltage. It has a DC level is This is now for off time. And then you can see here for off time, you have DC level on this capacitor, but it still has the same resonant ripple and a regular linear ripple. Okay. And I think I went through it yesterday, but just to confirm, which we, after 2010, it took 8 years before the industry came, this so-called power management industry, which really not managing power, they are managing devices. I call them device management industry. They are finally came to replace my switch, which at this in 2010, I told them I could use this. Where is it here? Yeah, in 2010, I told them I need the switch here, which is what this is 2010, not 2021. 11 years ago, I told the industry, please give me the voltage bidirectional switch, which works in the first and fourth quadrant, because you're a device manufacturer, you're not power management manufacturers. Give me that switch. They didn't give me that switch until Panasonic came in 2018 and said, oh, Dr. Ćuk, here is a MOSFET, here is a gallium nitride switch, which actually followed what you said 5 years ago, that you can use gallium nitride switch with the 2 gates, and therefore then you get this single semiconductor switch, which acts in both ways. What I had to do at the time, I had to two MOSFETs, which are current bidirectional devices, so you have to cascade them at the top of each other to disable operation in a, for each MOSFET switch is operating in first and fourth quadrant, so you have to disable operation in one direction, disable other. You have complicated drive. You know, Infineon was making the drive for this, which cost $100 to drive these 2 switches at the top of each other, right? And now you don't need that for this gallium nitride with 2 gates. And the other option is, this is a symbol for a gallium, this symbol for what is called, you see, the symbol here has a little, you know, I don't know if I make it bigger. You see what the symbol said? Here's a little diode, this bidirectional IGBT, right? And what the bidirectional IGBT says, it has a built-in semiconductor diode in addition to transistor. That's what this diode is symbol says. So that makes the switch to conduct the current. This switch conducts the current in this direction, positive direction, and blocks the voltage in a positive direction. But I put a out of phase in parallel, same, but in a different direction than this other S2 switch operates in the 3rd quadrant because it conducts the current in the 3rd quadrant and blocks the voltage in the 3rd quadrant, okay? But again, both of these switches are composite. MOSFET switch, it has 1 million ohm resistance and the other one 1 million. I have 2 million ohm resistances, whereas if I had a single switch and use these 2 MOSFETs, if they had a bidirectional capability, if I use them in parallel, 2 millions will become 500,000. So what happens? Not only I have a much more complicated structure, I have 4 times higher losses and 100 voltage drive for this, right? And why did it take industry 11 years to get to it, and they're still not using it? Because this Panasonic company sold their business because they didn't have a use for it. That tells you how bad is our power management industry. It is bad because they're not managing even devices properly, okay?